All right, so let's look at a couple of practice problems related to our equilibrium constant K. So here are two examples where we want to write the equilibrium constant expression with respect to partial pressure, so K sub P, for both of these reactions. So pause this video and go ahead and attempt both of these. So we have the following expressions. So notice for this first one, we have a solid and a gas as our two reactants that form a solid. And recall, for our equilibrium constant expressions, both our reaction quotient and equilibrium constant K, we do not include solids or liquids in our expression. So this is why we have one here for this first one. So solids are represented as one. They're thought to be pure. They don't change. Their concentration doesn't change. So we just plug in a 1 over the pressure of CO2, which is in a gas phase. And again, our calcium oxide would be represented as 1 as well. So this is 1 over pressure of CO2 is our K sub P expression. Similarly, for the second example, right, we have the partial pressure with respect to CS2 over sulfur, right, raised to its respective coefficient. We ignore graphite or solid carbon because it is a solid and it is represented as 1. Okay, so main takeaway here is just remember that we ignore solids and liquids from our equilibrium constant expressions, as well as our reaction quotient expression. So let's look at another practice problem. For this reaction here, we are given the value of K sub C and we are asked to find K sub P. So here is a problem where we can use that equation we derived that relates both K sub C and K sub P, right? This is our equation here. So we're going to plug in K sub C, the value that's given. R is our ideal gas law constant. T is temperature. And in this case, if ever the temperature is not specified, we will just assume that it is room temperature. It is room temperature, and we can plug in for delta N. So here is what we get. So we plugged in for K sub C. We have 0.0821 as our constant R. Room temperature is 298 Kelvin. And to find the change in our stoichiometric coefficients, we have 2 total in our products minus 1 for N2 plus 3 for H2. So it's 2 minus 1 plus 3 as our delta N. When we solve this, we get 1.83 times 10 to the minus 6 atmospheres to the negative second power. So these are our units for our K sub P expression. However, we don't usually use units. We don't have to express units for our equilibrium constant or reaction quotient expressions, right? But you can, if you plugged in all the units here, you would see how we got this atmosphere raised to the minus 2 power. But the reason I didn't plug in the units here because we ignore the units in this case. All right, so K sub C, K sub P expressions are usually written without units.